Welcome to the second video of this week, in which we have a brief look at general Markov processes with continuous state space. So let Xn be a stochastic process with the state space S being a subset of R. Then, assuming here that it's a process discrete in time, then Xn satisfies the Markov condition if, as before, Xn plus 1 so the Markov process at time n plus 1 is independent of the past of the process up to time n minus 1, given that we know the state of the process at time n, or expressed in terms of probability, and that is where we have a slight difference to the Markov property before. We say that the probability of the Markov process at time n plus n falling into a set A, given the full past of the process up to time n, equals the probability of the same event, xn plus 1 falling into the set A, given only the information about the Markov process at time n. So as before, the past up to time n minus 1 is irrelevant for predicting the Markov process at the next state, next time. But as we don't have a discrete process anymore, we don't have probability mass functions, we need general probabilities as a probability that this process takes a specific value would be 0. If the state space is discrete, such a process is called a Markov chain. That is what we discussed so far. Now, in order to prove that a process is a Markov chain, the following characterization as a randomized dynamic system is very helpful. So the stochastic process here satisfies the Markov condition if and only if Xn can be expressed in this form. So Xn is a function, possibly depending on the time, of the most recent value of the process and some random variable epsilon n that needs to be independent of the past of the process, including xn minus 1. So epsilon n can be seen as noise entering this dynamic system that is independent of the past, and otherwise xn depends on the past only through the most recent value. As an example, suppose that we're interested in repeated tosses of a fair coin. So xn equals 1 if head occurs in the nth toss and 0 otherwise, and yn is the number of heads in the first tosses. So we simply add these xi's and in this way count the number of heads in the n tosses. Because we can rewrite then yn, so we can split the sum into the first n minus 1 items and then plus xn. Now this here is yn minus 1, and in that way we have an alternative representation of yn as a function of the most recent value and xn, and since xn are independent identity distributed, xn is independent of the complete past of the process, and thus yn, this representation here, satisfies the conditions for the characterization as a randomized dynamic system, and we conclude that yn is a Markov process. It satisfies the Markov condition. Another example, an AR1 process. So here we have now continuous state space. So epsilon t are independent identity normally distributed, say, and xt is A times the most recent value xt minus 1 plus the noise epsilon t. And then because of this representation, we immediately see that xt is a Markov process. Alternatively, if you look at an autoregressive process of higher order, in particular autoregressive process of order 2. So we have here an additional term where xt depends on xt minus 1 linearly in this form. Then unless A2 equals 2, in which case, of course, we have the AR1 process, unless that is given, xt cannot be a Markov process. This is only a representation. We cannot rule out that we can find an alternative representation where xt only depends on xt minus 1. However, this representation here, of course, suggests that xt cannot be a Markov process. But in order to prove that, we have to look at the full conditionals. And here we, for instance, could think of looking at the probability that xt is smaller or equals 0, given that so we condition here on the Markov chain at time t minus 1, suppose that equals 0, and xt minus 2 taking a value x. Now, if xt were a Markov process, this should not depend on the value of x. Now, according to this equation here, this value then will be a2 times x. So we have a normally distributed random variable with mean a2 times x and variance sigma square. So the probability that this is smaller or equal 0 equals the distribution, the CDF of a standard normally distributed random variable at minus a times x divided by sigma. And of course, so that would be actually a2 times x. And as we vary x, we get here different probabilities for the probability that xt is smaller or equals 0. So that contradicts the assumption that xt is Markov, or it simply shows that xt cannot be a Markov process because we have found here a counterexample, and therefore xt is non-Markovian. However, we can convert this AR2 process into an AR1 process, and by that convert it into a Markov process. Namely, let yt be a two-dimensional process with states xt minus 1 and xt and xt minus 1. Then we can write yt as a linear function of yt minus 1, namely the first line here will give us the equation for xt, a1 and a2, where yt minus 1 consists of xt minus 1 and xt minus 2. So this here will be exactly this mean part of the equation. And here, the second component of yt is xt minus 1, and that is identical to the first component of yt minus 1. So here we have a simple 1 and 0 for the coefficients, and then we only have noise in the first equation, namely epsilon t. And now if we know yt minus 1, then yt no longer depends on the past. So this functional form here completely shows that yt is a Markov process. If you have time-continuous stochastic process, the Markov property cannot be as easily written down because we lack the notion of a next point in time. So instead, we have to look at any arbitrary point in time in the future, where we condition here on the past. So xt equals x, and then we have an arbitrary number of n time points. So any arbitrary n, we have n time points being somewhere in the past between 0 and t. And then if this condition probability does not depend on the past here, but only on the most recent value at time t, then, so these times here are in the past of this process. This is the most recent value from all these values. And then all the other values are of no relevance, and the probability only depends on this most recent value. If that is the case, then the process satisfies the Markov property. The very interesting thing is that it is sufficient to consider here an arbitrary but finite number of points in the past. And that is exactly due to the fact that we have this Kolmogorov theorem about the finite dimensional distributions, that the finite dimensional distributions of the process already characterize the distribution. And therefore, it is here sufficient not to condition on the full past in full at all time points in the past, but to look at arbitrary finitely many time points. More generally, we can, or equivalently, we can write the Markov property also in terms of condition independence. So again, here we have a point in the future. Here we have the process at time t, called that present. And then we have here the complete past, so where ftx is a sigma algebra generated by the complete past of the process up to time t. And this sigma algebra forms the information that we get by observing the past of the process. And the Markov property is satisfied if xt plus s is independent of this complete sigma algebra, so of all events inside this sigma algebra, given that we know the value of xt. This is already what I wanted to say about time continuous and continuous state space Markov processes. Thank you for attention.